The color sensor identifies colors according to the RGB model, which is a fundamental color model in digital imaging and display technology. Following this model, colors are created by adding light of the three primary colors, red, green and blue, in various combinations and intensities. Each of the three primary colors typically has an intensity value ranging from 0 to 255, where 0 means no light and 255 means full intensity. This table shows some basic combinations of full intensity and zero intensity of all three colors. Combining red, green, and blue light at full intensity produces white light, while a combination of zero intensity of all three colors results in black. The rest of the colors that appear in this table are important because they can be found in another color model, named CMYK, that stands for cyan, magenta, yellow, and key, where key is used for black. The CMYK model is used for printing colors. You can search the web for more information on these color models. For the purposes of this lesson, we have covered them adequately. As already mentioned, our sensor follows the RGB model. Up to now we have assumed that the maximum value for a primary color is 255. Well, this is true if 8 bits are used for storing this value. A bit is a binary digit that is either 0 or 1. Using 8 bits, the biggest number we can store is this binary number, which can be written as 255 in the decimal numeric system. Note, however, that our color sensor is the TCS34725, which uses 16 bits for storing the value of each primary color. The biggest decimal number that occupies 16 bits in the binary numerical system is 65,535. Therefore, the sensor detects any color in the form of three numbers that are between 0 and 65535. Let us now see the block commands for exploiting this sensor. The color sensor must be initialized before it is used. After the initialization, we can access the values returned by the sensor through this block. And now let us go to Snap for Arduino. First, we initialize the sensor. A sound produced by ODI informs us of the fact that the color sensor is now ready to be used. First, we are going to detect the color of the floor. Here, ODI is placed on a white surface. A first observation is that this color is not equal to the white color as we know it in the RGB model. First, we can say that what we see as white differs from the theoretical white, or said otherwise, the absolute white. Second, the values of the three primary colors returned by our sensor depend on the light conditions. The stronger the light, the bigger the values. The light conditions are mostly due to the LED within the color sensor. However, keep in mind that external light also plays a role. To minimize the effect of external light, the sensor must be placed as close to the floor as possible so that external light cannot infiltrate the area of detection. We have now turned ODI 90 degrees on the same surface. Since the surface is the same and the external light is the same, one would expect that the returned values will also be the same. Well, this is not true. The returned values are now different. Perhaps the external light is not exactly the same now, or perhaps the surface does not have exactly the same color everywhere, but instead, minor color variations invincible to the eye exist. Whatever the cause of this fact may be, it is a fact and you should have it in mind. And now, something even more troubling. We click again to detect the color of the same surface, without moving ODI at all. If you check the value of the blue color, you will see that it has changed. It is a minor change, but still, a change. What we have done so far is to interact with the piece of hardware called color sensor, and it turns out that this piece of hardware is far from easy to exploit. Its main problem is that it is oversensitive. To simplify its use, we have provided the user with an improved functionality over the sensor. This improved functionality is based on the following requirements. First, we want the sensor to return a color, for example blue or yellow, and not numbers. Second, we want the sensor to be sensitive enough so that it does not confuse colors and not oversensitive, that is, slight variations of a given color should be identified as the given color. This functionality is realized through specialized block commands and is based on a set of defined colors which we call basic colors. The colors in this set are green, red, blue, cyan, magenta, yellow, black, white, and fluor. The user is able to activate or inactivate basic colors in a straightforward manner and then match the colors of real objects to the activated basic colors. For example, if the user has a piece of paper with a color identified as blue, the user is able to store the values returned by the sensor when detecting this color as the basic blue color. The basic blue color is then fixed. The user does not see the actual values of the color, and this is exactly what we want, that is, colors instead of numbers. Any detected color can be matched by ODI to the closest activated and fixed basic color, as long as this basic color is close enough. The user is able to define what close enough means by setting a parameter. Let us explain this in more detail. Assume that when we fixed blue, the values stored in ODI's memory were 350 for red, 400 for green, and 1600 for blue. So, this is our basic blue. Let us visualize these numbers like this. We now define a parameter, called similarity frame, the value of which is a percentage. Thus it must be between 0 and 100. If it is set to 0, then in order for ODI to identify an object as blue, the values of the primary colors for this object must be identical to the stored ones for the basic blue. Therefore, this color will not be identified as blue. This is because the value of green for this color is not identical to the value of green for the basic blue color. By setting the similarity frame to be bigger than 0, we create an interval that includes the values of the basic blue color as follows. Let us set the similarity frame to 10%. Starting from any of the three values corresponding to the basic blue, we create an interval that starts from the value minus 10% of the value and ends at value plus 10% of the value. For example, if the value is equal to 300, this interval is from 270 to 330. Here we see again the values for the basic blue color, but in advance, we see the intervals created by the value of the similarity frame. This color will now be identified as blue, because all three values of the color fall into the intervals of the basic blue color. This color, however, will not be identified as blue, because its value for green lies outside the interval corresponding to the basic blue color. If we want this color to be identified as blue, we need to lengthen the intervals, and we can do that by increasing the similarity frame. Now, this color is identified as blue. Keep in mind that the basic colors must be distant from each other in order for this framework to be efficient. If we have two basic colors that are similar, then it is possible for their intervals to intercept each other in all three primary colors even if the similarity frame is small. For example, let these lines be the values of a basic color, and these lines be the values of another basic color. Here you see the intervals of the first basic color for a given value of the similarity frame. And now you see the intervals of the other basic color for the same value of the similarity frame. The rectangles visualize the areas where the intervals of the two basic colors intersect each other. Now, the color indicated by these arrows cannot be identified because it can be either of the two basic colors. To avoid such a problem, do try to follow the names of the basic colors. In particular, try to use a bluish color as blue, a yellowish color as yellow, and so on. This undesirable phenomenon may also occur if the basic colors are distant but the similarity frame is too high. The right value of the similarity frame in each educational scenario must be found by the user via a trial and error approach. It is now time to show how all this stuff works in Snap for Arduino. We will use three basic colors, blue, yellow, and white. We will use printed pieces of paper for blue and yellow, and the floor for white. Before we use the sensor, we have to activate the involved basic colors and inactivate all the others, and then initialize the sensor. The corresponding blocks are in the configuration category. As said, we activate only blue, yellow, and white and inactivate all the others. Done. Then we have to fix the activated colors. Now, the surface below the color sensor is white and we will fix the white color. Done. Next, we place the blue piece of paper below the sensor. Now we fix blue. Done. Finally, we place the yellow paper below the sensor and fix yellow. Done. Let us now see if we can detect the colors. For the block command to work, we need to set the similarity frame. Note that this scenario is almost ideal because the light conditions are stable as a result of the fact that Odie is not moving. Setting the similarity frame to 10% will suffice. Keep in mind, however, that when Odie is moving, things change and we may need a bigger value. Let us now detect the white color. You see that the result of the block is not a triplet of numbers, but it is the name of a basic color. Odie has recognized white. Or, to be more precise, it is concluded that the detected color is closer to the basic white than to the other basic activated colors, therefore it has been identified the detected color as white. Let us now see if we can successfully identify yellow. Done. It remains to see if we can successfully identify blue. Indeed we can. It follows that setting the similarity frame to 10% was a good choice after all. If we had not been successful in recognizing the colors, we would need a higher value. Now we will see a more advanced educational scenario that uses the color sensor. It is more advanced because we will use lists. We call it the color collector. According to this scenario, Odie collects colors that have not been detected. We will store the collected colors in a list. Odie will stop when all the activated colors have been collected. As before, we have colored pieces of paper and we have placed them on the floor. In this instance, we use 3 colors. Odie will move as the arrow shows, with its color sensor facing down. Initially, the list of collected colors is empty. Each time Odie detects a new color that has been activated and does not exist in the list, this color is inserted into the list. Odie stops when all the activated colors have been inserted into the list. In this example, the activated colors are yellow, red, and blue, and Odie will stop when it detects the blue color. This is the code for the color collector scenario. Initially, the previously created variable, named color list, is set to be a list. Then we set the wheels for moving forward. Observe that the 2 wheels do not have the same speed. This is because we have set the speed of each wheel in such a way so that Odie moves straight forward. We have discussed this issue in Lesson 1. Then we have a loop, which will end when the length of the color list is equal to 3. Note that the length of a list is the number of elements inside the list. Observe that there is at least one color in our scenario that we have not taken into account. It is the color of the floor. We have chosen not to activate and fix this color. The idea is that since this color is quite distant from the activated basic ones, Odie will not be able to match it to any of the activated colors. In this case, the returned color is unknown and we have covered this case in our code. Each time the loop is executed, we access the color corresponding to the numbers returned by the sensor. We store it in the variable named detected color. The detected color is either one of the basic and activated ones or unknown. If the detected color is not unknown and if it does not already exist in the color list, we add it in the color list. Let us now see the execution of this program in Snap for Arduino. Once again, we have to mention that before this execution, we have activated and fixed the in bold colors. Do check the elements of the list as Odie moves. And this concludes Lesson 8.